right, so here we go. Last one of the year.
Yay. Don't tell us that.
Yeah, I don't think that's true necessarily.
If you stop reminding us, we might forget to actually focus.
Okay.
Okay.
All right, so electrolysis, and I basically said this earlier today, I think. A voltaic cell is you set up this reaction so that the electrons can spontaneously flow from the anode to the cathode, from the thing that's getting oxidized to the thing that's getting reduced. And this just happens. All you have to do, and you guys saw this in the lab that you did, all you have to do is basically connect one cell to another, and the electrons will spontaneously flow. Electrolysis is what you do when you want electrons to flow, but they're not going to go in the direction you want them to. All right? So there's a couple of times you might want to do this. One is the recharging of a battery, which we've already kind of talked about. Okay, that pushes the electrons back in the other direction from the way that they spontaneously flowed to begin with. The other one is with electroplating. When you want to get a certain metal, you still leave it. When you want to get a certain metal that maybe is hard to get otherwise. Okay, an example of that might be like sodium metal. Now this is not the best diagram for this. Let's see, we've got sodium chloride. And yeah, I'm not even sure. See, the one that's in the book I like better because, and I wish that I had that picture. Let me make sure that I don't here. I don't think it's on here anywhere. No, it's not. Okay, so I'll just kind of draw it, I suppose. But basically, what is in the book is it's showing NaCl, and you've got your voltage source. Okay, so when you have these, a lot of times you'll just have kind of a big compartment like this. So you can already see it's a little bit different than the voltaic cells. And in order for this to work, you're going to need molten metal, okay, or molten, I guess, the ionic compound. So like, let's say that we want to get sodium, okay, because sodium's fun to play with. Not play with, really, but sodium is fun to do demos with in science classes, so it's useful to have solid sodium for certain things, not just for that, but in order to get that sodium, you're not going to be able to find sodium that's unreacted anywhere in nature because it's so reactive. It will have already reacted with oxygen in the air or, an anion that comes floating by. So you have to basically make the solid sodium, and one of the ways to do that is through electrolysis. So what you can do is you can take sodium chloride, get it really, really hot until it melts, okay, which you're going to have to get a pretty high temperature there. But you're going to melt it, so now you've got molten sodium and chlorine ions, chloride ions, running around inside the solution, okay? So now it's molten in here, and you've got your Na+, HCl minus running around, okay? And then what you do is you put in your electrodes, just like we did with the voltaic cells, okay? And then you run wires between the two, but instead of putting a voltmeter that detects voltage here, you put a voltage source of some sort. I'm not sure what to put here. I'll just put, I don't know, battery, okay? It's probably not a battery, but something that has a voltage, right? Oh, yeah, there we go. So it can be a battery. I don't know. For this one, you might need something that's a little bit stronger than that. Yeah, you might. Anyway, the point is, you're going to have some sort of voltage source here, okay? And what it's going to do is it's basically going to push the electrons through this thing, okay? And when it does that, it kind of forces things to go in the opposite direction that they would normally go, all right? And so then, as the electrons are flowing through, see, I put these on the wrong sides based on the direction of my arrows. We've got sodium and chlorine, everywhere in this thing, but I'll just put the sodium over here and the chlorine over here, okay? And so then what ends up happening is the sodium, the Na+ is going to gain electrons as the electrons come through this side, through this electrode. And then you're going to end up with solid sodium starting to plate out on this electrode. Okay? So then you get the solid sodium. Now on the other side, the chlorine is losing electrons, so what's going to happen to the chlorine? If it loses electrons, it's getting oxidized, right? So then it's just going to become chlorine. So then you end up with chlorine gas. This is a really safe thing to do, by the way. You know, you're making solid sodium, chlorine gas in molten salt. You know, so yeah, you wouldn't hurt yourself if this happened. You have to be careful with this sort of thing. Obviously, this is not something that can happen in a normal high school chemistry lab, right? But that's what's going to happen there. So you're basically pushing the current through in the opposite direction of the way it normally would go, and you're forcing these Na+ ions to actually become solid sodium. Okay, so you're forcing the sodium to get reduced and the chlorine to get oxidized, which obviously is a little bit against the grain of what would normally happen with those two things. Okay, but you can do that if you put a voltage through a solution. Now, you might think, well, there's a much easier way to do this, right? We don't even need to use molten metal. If you put sodium chloride into water, it separates into its ions, right? Okay, so let's try this in water. So then you got your voltage source. Okay, now we've got H2O running around in here, and we've got the sodium. Well, here, I'll put the sodium where I put it before. And we got the sodium, and we've got the chlorine, okay? So it seems like that would work. Let's run a current through it, okay? Well, here's the problem. The water is kind of going to steal the thunder of the sodium and the chlorine, right? The sodium is so far away from wanting to get reduced that the water will actually get reduced first, okay? And if water gets reduced, you can look on your reduction potential chart. I have one handy. Of course I don't. Let's see, I can look in the book, I guess. So if you look at your reduction potential chart, thank you. When water gets reduced, it's going to turn into hydrogen gas, right? And so that is going to happen before sodium does, because if you look at that reduction potential, water has a higher potential for being reduced than sodium does, okay? And so what happens is, because we've got water in this thing, you end up making hydrogen gas at this electrode instead, okay? At the other electrode, if you look at the chlorine, that one's going to get oxidized, okay? But if you look, the oxygen here, or the water, sorry, we got to flip this. The water is going to have a higher tendency to get oxidized than the chlorine, so you're actually going to end up making oxygen gas at this electrode, okay? So the water sort of short-circuits the process, so unfortunately we can't just put salts into water most of the time. Now, sometimes that will work, depending on where the water is on the chart compared to whatever ions you've got in there. But for sodium chloride, it definitely does not work. All right. So you you run a current through salt water, you're going to make hydrogen gas and oxygen gas. Is what you're going to make, which is. Well, that's true. I guess if the sodium plated it, yeah, I didn't even think about that. If the sodium did plate, it would immediately react with the water. Yeah, that's going to start to heat up your reaction, and then you're going to have hydroxide running around in there, so that complicates things. But yeah, anyway, point is, it's
That little diagram of your example of the NaCl aqueous, and then you
maybe that's what they were trying to show there.
NaOH.
Well, except you've got the H2 gas, but then the Cl2 gas. No, I don't. It's not going to make chlorine gas. It's going to make the oxygen gas. I'm pretty sure.
Miss Mitch Richter Cussing, please report to the attendance office. Mitch Richter Cussing, please report to the attendance office. Thank you.
They don't specifically say it in here. They do it for a different reaction. So I think I'm right on that, though. I'm pretty sure. I'll double check later. Point is, water complicates things. Okay, that's the main point that I'm trying to make here. And you don't really have to. You're not going to be asked a question on the AP exam where they ask you, you know, what exactly is happening here. Okay, but you do need to know that water complicates things, and you need to be able to compare water's reduction potential and its oxidation potential to these other salts that are in there, and be able to tell what's going to get oxidized first and what's going to get reduced first. I guess we were talking about this before we started the video. I guess this other drawing here is just showing that you can use this. Now I'm not sure why they show it with a silver spoon necessarily, because there's much more practical things that you could be discussing rather than a silver spoon. But if your silver spoon needs to be replated with silver because somehow some of the silver wore off or oxidized, I don't know. I don't know why you would need more silver on your spoon. But if you did, you could do this, okay? You could put a silver electrode in, you could dip your spoon down into this solution that has the aqueous AgNO3, and if you pass a current through it, you could get the silver to plate out on the spoon. So, just in case you've ever wanted to do that, I don't know. Yeah. If you wanted to smuggle silver out of here, I guess that's how you could do it. Bring in your spoon, dip it in the water, use my silver that you used for that last electrochem lab, and I'll just be left wondering why my silver strips are getting thinner and thinner. I don't know. Okay. Yeah. All right, and then there's an even bigger picture of it, just in case you wanted to see that. So basically what you need to understand about electrolysis is we're using electrical energy and we're pushing it in the non-spontaneous direction, okay? The AP curriculum does make a big deal about this. There are certain ways that you can make non-spontaneous reactions happen. Electricity is a big one, okay? So we'll use this electrical energy and we'll push the reaction in the opposite direction. It's used for electroplating, electrolysis of water, which we just talked about, okay? Electrolysis of water, separation of a mixture of ions. So there are several reasons that you can use this, and this is kind of what I was saying before too. The most negative reduction potential is the easiest to plate out of a solution. So the more negative the reduction potential, the easier it will be to get it to plate out on the spoon or the piece of metal, whatever you've got, because it will be easily oxidized. If it has a negative reduction potential, it's easily oxidized, right? Okay, so then to calculate this, they have a totally different set of calculations that they introduce with electrolysis. The thing is, you can do this with the voltaic cell too. I'm not sure why they wait to introduce the calculations, but we'll talk about it in the context of electrolysis, and then maybe I'll mention a little something about how you could use this in the context of voltaic cells too. Yeah, this is covering your thing here. But this flow chart is also in your book on page 878, and I think this is probably pretty useful for you. So a lot of times what they'll give you at the beginning of this problem is they'll give you a current. Here's the current we're passing through the electrolysis apparatus, through the solution, through the whatever it is. And here's how long we did it for, okay? If you know current and time, you can use this formula right here, Q equals I times T. This is on your equation sheet for the AP exam. Q is what? Any ideas? In this context, physics people help me out maybe?
Oh, it's charge.
Charge. Q is charge. I is current. So charge is going to be measured in coulombs. Current's going to be measured in amps. And T is time, and that's measured in seconds. Okay? So if you know those things, then you can, if you know the current and you know the time, then you can solve for the charge. And once you know the charge, you can use Faraday's constant as a conversion factor, okay? Because if you know the charge, and you know that Faraday's constant is 96,005, well, let's see, I'm rounding now. It's 96,485, is that right? Okay, 485 coulombs per mole. Okay, so now you have a nice conversion factor, and this is per mole of electrons is what this is, okay? So once you know how many coulombs you've got, once you've found your Q, then you can figure out how many moles of electrons have flowed through there. Once you know that, you can compare it to that. You can do some stoichiometry then. Look at the balanced chemical equation and figure out if you've got this many moles of electrons, how many moles of whatever am I making, and then change that back to grams. Okay? So if you know your current and your time with electrolysis, you can actually figure out the mass of whatever substance it is that you can plate out in a certain amount of time given a certain amount of current. Okay, so that's the basic calculation here. I don't think it's going to give you all that much trouble, especially since you get this formula. So as long as you get to Q, it's really not that bad. Then you just use your Faraday's as a conversion factor, and then you do normal stoichiometry at that point. Okay, so this kind of walks you through that. Find the product of the current and the time. That'll give you the charge. Use Faraday's as a conversion factor. That'll give you moles of electrons. Which, just a side note here, for some reason, it seems like on the AP exam in the past, they have used Faraday. How many Faradays? Almost synonymously with moles of electrons. Okay, so if you get asked that question, like how many Faradays are there, they're looking for how many moles of electrons do you have. Okay, which a little weird. I'm not sure exactly why they do that, but that's how it's been done in the past. Use the coefficients in the balanced equation to find your mole ratios. That'll give you moles of product, and then from there you can figure out grams, liters, number of molecules if you want to, whatever we normally find out with stoichiometry. Okay. Mass of metal plated, Faraday's constant. I'm not sure why they're writing all this way. Just listen to what I'm saying. I think it makes more sense. A volt does equal a joule divided by a coulomb. See, the thing is, the book does go on to talk about how you could calculate the work done in joules. So, but I've never seen a question on the AP exam about that. It's not in the AP curriculum, so I'm not worried about that. All right, so here's an example. How many grams of copper are deposited on the cathode of an electrolytic cell if an electric current of 2.00 amps is run through the solution of CuSO4 for a period of 20 minutes? Okay, so, well, eventually we're going to need an equation, right? But let's just kind of walk our way through this thing. We've got a current, and we've got a time, right? So we can use that to find our charge, right? Q equals I times T. That's a Q, sorry. So our charge is going to be equal to our 2.00 amps times what? Yeah, you have to be a little careful here. It's 20 times 60, so it's really sad that I can't do that in my head. 1,200?
Just take off zeros and do 6 times.
I know. I just panic when I'm making the videos. Okay, so 12 times 1,200 seconds. Okay, so that's going to give us a charge of 2,400. Well, that's technically 1 sig fig. I'm just going to do 2. I think that's a little strange here. Here. There we go. All better. Okay, so 2,400, what? Coulombs, okay? So now we've got it in coulombs, right? So now what we can do is use Faraday's constant, which will get us from coulombs. Well, see, I'm going to need more room here. Oh, well. I'll just do it in several levels. There are 96,485 coulombs in 1 mole of electrons. All right? So that gets us from coulombs to moles of electrons. Yeah. And then we're going to go from moles of electrons to, to what? Yeah, moles of copper, right? Well, now we got a problem because we don't have an equation, okay? Now, you can make the equation at the beginning, or you can wait till this step until you realize, oh, I need an equation, and then make it. Doesn't really matter, okay? But we've got to figure out what's happening in this equation, all right? Copper is being deposited on the cathode. So what would our half reaction be here? We're probably starting with Cu2+. Now, actually, not probably. That's why they give us the CuSO4 thing, so that we know this is copper 2+ we're dealing with. All right? And the copper 2+ is going to change to, it's going to just change to solid copper, okay? Now we got 2 electrons here, okay? And I think that's pretty much it for our half reaction, right? So for every 1 mole of copper, we have 2 moles of electrons. Everybody okay with that? And then we'll go from moles of copper. They're asking about grams of copper, so then we'll go to grams of copper. In 1 mole, there are 63.546. Okay, so then you work all that out, and that's going to give you your answer. All right. So run a 2 amp current through for 20 minutes, and you get 0.79 grams of copper. Yeah. We're rich.
Well, 2 amps.
Yeah, you might
Through, that's like,
you might want to pass a little bit higher current through there.
okay.
But that's what you would get if you passed a current of 2 amps through the copper sulfate for a period of 20 minutes.
Why not add an extra step and do it like, oh, you run this many volts through it, and this how much resistance and it costs, and that's 5 amps.
Yeah, you could do that, but then we're in physics instead of chemistry. Which, I mean, honestly, they're very closely related.
Which one's more important?
Which one's more important? I'm not going to make a comment there because I'm afraid of what might happen to me. All right. So then the next one here, how many hours would it take to produce 75 grams of metallic chromium by the electrolytic reduction of Cr3+ with a current of 2.25 amps? All right. So 75.0 grams. So now they're starting us with a mass, and they're asking for time. So we're basically going backwards here. Let's go ahead and do the equation first, because we're going to need that right off the bat. The reduction of Cr3+. And that's essentially what was happening before, right? They just didn't call it a reduction in the other part. So Cr3+, I'm going to assume solid chromium here.
Yeah,
because it could be reduced to a 2+, but passing a current through it is probably going to reduce it to its lowest possible state. Oh yeah, it does say metallic chromium. That's right. It's solid. We're talking about electroplating here, so that's another reason. Okay, so there's our reaction. We've got 75.0 grams of the chromium. Grams to moles. Now we're back in stoichiometry all of a sudden. Chromium is 51.996. We're going to go from moles of chromium to moles of electrons. And for every 1 mole of chromium that's plated out, there are 3 moles of electrons. So then we'll go from moles of electrons to coulombs with Faraday's constant, 96,485. And then we're probably done at that point. I guess we could do the other part as a conversion as well. But I'm going to do it this way just because this is the way that they give you the equation on the equation sheet. So we've got 75 divided by 51.996 times 3 times 96,485. That's a large number. So we're getting 417,000 coulombs. Let's see, what? Yeah, that's right, isn't it? 418,000 coulombs. Okay? So then, remember our equation here. Sorry, I started with the wrong thing. Q is equal to I times T. So if we want to rearrange that, because what we're solving for here is time, so time is equal to Q divided by I. So 418,000 divided by 2.25. And you're right, this is going to be a long time. I'm actually going to use my unrounded number because that way we won't round till the end. So I'm getting 186,000. Now remember, that's seconds, so that's not as bad as it seems. Okay, but if we want to figure out how many minutes or how many hours, oh, it asks for how many hours. So now we've got to do another conversion here. And I rounded too soon. Well, let's just go to hours. We can do that, right? You guys are okay with going straight to hours? That's how I would make my chemistry students do it, but... Okay. That's going to make our number a little bit nicer here. Still going to take 51.5 hours. Yep. That's a long time. I mean, it's not excessively long. But that's how electrolysis works, and that's the kind of problem you're going to see on electrolysis. Does that make sense? So I don't think it's all that difficult, but it's just the total opposite of what we've been learning for the rest of the chapter. All right, that concludes our last video for the year.
I cannot be the last one. I will be the first one.
I don't know what to say to end this. I mean, it's been a wonderful year. Thanks for everything, everybody.
I'd like to
Thank the Academy. I could just keep talking, but I'll cut it off. All right, see you later.